All right. So if we're tuning in later, okay, this is probably the third or fourth time I've explained this, and that's fine. There's 10 questions, I think, that will be associated with this Revolutionary War video and the technology and concepts like energy that we're doing now. So 1 through 8 is what we made yesterday, okay? And I think just verbally we just said what these were, and if you wrote them down, fine. If not, now's your opportunity. 9 and 10, I don't know if we'll get to those today, but then these are new story problems, and we'll go over those later on today. So again, if you're tuning in later, it's maybe about this time you'd want to hit pause so you can see this, because, oh, animals with paws. Is that a coincidence? Rawr! Rawr. Oh, okay. Anyway, I'm going to ask one question. I bet you all think the same thing. And I don't want to give it, well, I might have to give you a little bit of a clue. But when you see this, what is the first thing that comes to mind? Cat. I think I heard it over there. What was that?
Oh, the Lion King.
Okay. But yes, who said, so it was over on this side. I just couldn't tell who. Someone said Lion King. Okay. So, do you know how many of you like the movie The Lion King? You do realize that it is 21 years old.
Yeah.
Is my math right? 1994, I think it came out. So, oh gosh, well, I don't know if that makes us feel any better, Mrs. Carroll. It really doesn't. But, okay, so does that surprise you that that it's 25 years old? That it, 2004 to, oh, it's 30 years old. Right? Did I say 25? So now it makes us feel even worse.
Yeah, it does.
Okay. But let me ask you this. Tonight on, this is probably more so for women, I don't know, maybe for the guys too. Tonight on NBC, because sometimes we watch the news on NBC, they got commercials that Wicked is on tonight at 7 on NBC. Now, the reason I bring that point up is I think we could say, what does a prequel mean? What does that mean to you?
Like it comes before.
It's something that comes before something else. So in this case, how many of you know the original Wizard of Oz? Okay. I'm just curious, and I might not know the correct answer either. When did that movie come out in your estimation? It was before World War II.
It was like 1952 or something.
Like 1928.
So 1928 is a better answer than the 50s. Oh, no. Because I said prior to World War II. So it can't be in the 50s. It can't be in the 60s. So with that, I want to say 1935. Okay? So my question is, when you see the movie Wicked, does that change your perception on the original Wizard of Oz?
1939.
Okay, so it was right the first time, 1939. Okay? So what U.S. state is associated with the Wizard of Oz? It is Kansas. That's right. Okay. Anyway, enough of that. So back to this, because when I think of that, I think of two things. Yes, the Lion King. And do you have a bad perception of that?
Yes.
Hyenas.
And Scar's little henchman.
Okay? But you also have to keep in mind that a reason a lot of these animals are around is for different ecological reasons or relationships, because these are what we could say take care of decomposing materials that are out on the open plains. Yes, they're scavengers just like many other animals, But these have capitalized on that. That's why they live in groups. Well, so do lions. But we could say that these are probably more heavily populated, but they do serve their role within any ecological community. But anyway, I was just wondering if you think the same thing when we say lion and you think Lion King, and then hyenas. I don't like those animals, you might think, but yes, they do serve their purpose. So what is the kinetic energy placed into a hyena when a 320 kilogram lion pounces on the animal from 4.10 meters away in 0.81 seconds? We'll come back to that later. So while holding a 100 kilogram barbell still, how much work are we doing? Zero, because it's not moving. What is the potential energy if the barbell is 1.55 meters off the ground? So I would presume that 1 meter is probably, so it's probably about right here. I mean, 180 kilograms, well, that'd be, these are too small for me because I usually have the 110-pound barbells. I sure hope you don't believe that. I'm not He-Man, okay? So anyway, getting back to what we need to go over.
Wait, Mr. McKinney, every time you say something like, anyways, back to something, you should say back to simple machine.
Back to simple machines. I don't know, because it's simple. Oh, okay. Back to simple machines then. I don't know. All right. So what are some different types of energies that we have discussed that is also part of this Revolutionary War technology? Kinetic is one. Potential, because they're up on the board. There are two more. Thermal and chemical. That's right. Okay. So now, my presenter here, I always try to put that back in the same place every time, but I just epically fail all the time. Yes, that is your kinetic energy formula. The kinetic energy equals, now you can write it like that, but I actually have my own perception on how I use that formula because that's what works better for me, okay? Just because I use it in a specific manner doesn't mean that you would have to use it in the same manner. It's just a suggestion. No wonder I couldn't see it. It's right here. Okay. At the most important aspect we want you to know is if we're not asking what is the potential energy, what is the kinetic energy, like what we are here, what do you think you can tell the difference between potential and kinetic? Kinetic has something in it that potential does not, because mass is going to be into the potential energy formula, and it's not the fraction. That could be a constant in any formula. But what do you think kinetic energy is doing that potential is not? Has something to do with this. If something has a velocity, you could say, well, we've talked about initial velocity being 0. We can put that in here. But if we do put 0 in for a velocity, how much energy would we have? 0, because you're multiplying everything by 0, so you're going to have nothing. Okay? So therefore, if something is moving, we know that we're dealing with probably kinetic energy. Now, that could be a result from thermal energy. That could be a result from chemical energy. That's where talking about these different types on how these flintlock weapons would work, whether it's a long rifle or that of the Brown Bess or the Colonial musket. That's the word I was looking for. Okay. So potential energy we would look as being a type of stored energy. Okay. And an example of that would be I had a rubber band laying around here somewhere because somebody left it behind. And now I don't see it. Here we go. So this picture, if we have a rubber band, notice we can stretch that. Yes, this is kinetic energy here, but the reason that this recoils is because that energy is stored within this rubber band here. Okay? So that's what we mean by something is stored, it's going to be kinetic energy. Okay? Does anyone want to take a guess? And maybe my perception is going to be wrong as well. But believe it or not, I don't mean to pick on us because we've already done that with our ages already. How many of you are able to park your vehicle inside? Okay. Is it in a garage? Okay. Now, believe it or not, that garages did exist without garage door openers. You do realize that, right? Okay. It used to be when we wanted to put our vehicles away, you pull up to there, you got to get out, got to open the door, put the vehicle inside, and then close the doors. Probably a distant memory for some of you, but that's fine. Or you might park it in a shed where maybe the doors slide side to side. But anyway, the technology in manual garage doors and even automatic garage doors, there's something that we could say that they also have potential energy in them. Do you know how these automatic garage doors work? You have a motor, that's true. The motor is pulling up on your door. So once you want to close your door, how does it know how to close? There's something above the entrance of the door that you probably never really thought of. Well, that's going to be attached to your garage door opener. Okay? It's something that we could say, okay, like inside of a pen like this, there's springs inside of there. Okay? So they're actually inside, well, you probably can't see this. Yeah, we could take it apart. But inside here, there's certain springs located, or they're located in here. So once you press another button, how does this part of the pen know how to go back up to the top? Well, there's springs in here that have energy stored in them. So that would be a type of potential energy. Okay? But getting back to these garage doors, your opener is pulling it up. Okay? But once you hit the button, your opener is, it's letting it go, but it's not going to pull it down. Something else is doing that. It's actually above your door up against the wall, and it's something that's wrapped around, and there are types of springs. Okay? Now, it would be my recommendation, and I think your parents would probably agree, if those need to be adjusted, you probably don't want to do those yourselves. I'm not saying that you can't, but even I'd like to think I'm somewhat mechanically inclined, but that's something I probably would not want to do because there's a lot of stored energy inside these garage doors. And even if you live on acreage or even here in town and you have, rather than the standard 7 or 8 foot garage door, maybe, I know there's one across the road here, I don't know who lives there, but I think that's probably a 12 to 14 foot garage door. Okay? So those springs have to be quite large in order for that to work properly. Okay. So then we're talking about potential energy then. Okay. I think, okay, we can talk about that tomorrow. The reason I wanted to mention these is because how do you know how to solve for anything if you don't know what the formula is? It's probably a good question, and you don't, and you can't. Okay, Well, you can. I mean, that's possible. But for our purposes, for kinetic energy, I would add this to your formula sheet. Ke for kinetic energy equals an object's mass times what? Velocity what? Squared. Now, you can write 1/2 mv squared, but what I choose to do is put this all over 2. Okay? And if you want to write it like this, you're still just fine. That's what the author chooses. These are the same thing. So how do we know that these are the same thing? What about if we put 4 in for a mass? If you put 4 in for this, or 4 in for this, what happens when you take 4 and divide by 2? What do we get? You get 2. What happens if you put 4 in for this and you multiply by 1/2? You get same thing, 2. So I use this one, and if you are more comfortable with that, that's absolutely fine. So then potential energy, we had established earlier, we know that mass is associated with that. Okay? Then what variable might this be, 1.55? Well, it's meters, that's the label, but the variable would be, it's the distance or how high it is off the ground. Okay? And then what is it that gives this barbell, this is a mass, it's not a weight. How does this get a weight from 180? It's from gravity. So the mass times gravity, or 9.8 times the height, that gives you your potential energy. If you wanted to put D in here, that's fine too. Okay? You could say PE equals mgd, okay? Or the author has mgh. So these are the 2 formulas that you can use. Okay? So now, what we mean by this is, so what is this kinetic energy placed into the hyena? So then, what are we up to now for the 33rd time? Okay? For the 33rd time, we've read the problem. The next thing we should do is write down our variables and what we know in the problem. Because on your assignment tomorrow, there's a question that deals with, I suppose, some of you deer hunters out there, that if you're not using a rifle, you're using a bow, where you have to solve for one type of energy, probably the potential energy, and place that into the kinetic energy formula, and then solve for whatever it's asking. Okay, so what do we know in this top problem? Mass is 320 kilograms. Okay, we know the distance is what? Okay, and then we know the time is 0.81 seconds. So what is the question really asking? Now, I want you to think about, even before we go any further, what do you think is probably the number one mistake that students will do? There could be 2. There's actually 2. But what do you think, looking at this formula, what do you think is the number one mistake students will forget to do? They're going to forget to square this, because that's what the formula is telling you to do. Okay? So once we cleared that hurdle, what's the next thing that might be a mistake that could be made? They might forget to either multiply by half or divide by 2. So now, what we need to do is what the formula is telling you to do, and that is, okay, our KE, because that's what we're looking for, equals our mass, which is 320. Okay? And we have to multiply that by what? Okay? Well, can we put anything there yet? Right. So we have a distance and we have a time. So with those two together, what can we solve for? Solve for your velocity. So 4.1 divided by 0.8 gives you approximately what? You get 400 and, oh, I hit 404. I didn't mean to do that. 4.10 divided by 0.81. That gives us approximately 5.06. Now, what you could do, we can write 5.06 in here, or what could you do with that 5.06? Okay, now this is what I'm talking about. We can write 5.06, okay, and then we got to remember to square that, okay? Or we can take that 5.06, take it times itself, and we could write 25.60 in there. You have to do one or the other, okay? So we'll go ahead and write that in as 25.60. Okay? So now our order of operations would say 25.6 times 320, and then divide that by 2. So we have 4,096. Okay? So our KE equals 4,096. Now, it's energy, so that energy will be labeled in what, do you believe? One letter, not newtons. Whoever said joules, that is correct. All energy is labeled in joules. Okay? Now, our next problem. Oh, front row, are we on the bus here? That just means, do we understand when I ask if we're on the bus? It's either this or we nod our head yes. Okay? Back row, are we on the bus here? Okay? And middle row. All right. We said we have this barbell and it's that far off the ground. We've read the problem. Again, the next thing we should do is, we know the mass is 180. Okay. Then we know our distance or our height. Okay. Same thing. 1.55 meters. Okay. There's a variable in that formula that's not written in here. In gravity, it also has a value of 9.8 meters per second squared. Okay? So then what is our potential energy? We don't know. So with these three numbers, do what the formula tells you to do. You multiply them all together. So we get 9.8 times 155, 1.55. And we're not talking about Paul Bunyan here, okay? Times 180. It gives us 2734. Potential energy equals 2734 point, is it 220. Again, it's a type of energy, so it's labeled in joules. Okay, so that's an example of both types of problems. Back row. And middle row. And front row. All right. So one last thing. I'm just going to erase this quick, and then the rest of the time will be yours. I'll go ahead and read this. It's a different type of problem that sometimes you're solving for a variety of variables. So if a volleyball has 3,121.2 joules of energy moving at an opponent, how fast was the 1.35 kilogram ball moving? Okay, so there again, once you have maybe made the decision to write it down, give you a little bit of time to do that. Okay, so for the 34th time now, what should we do next? Of course, write down our information. So what do we know in this problem?
Joules.
Okay, which means energy. Okay, and how do we know that it's kinetic energy? Because it's moving. Because if it's not moving, we know that it's potential. All right, so the kinetic energy, and it doesn't say that the kinetic energy is this. We just know that it's energy because it's labeled in joules. So we have 3,121.20 joules acting on that ball. Okay? So then what else do we know in the problem? The mass is 1.35 kilograms. So then what is the question ultimately asking? Okay. Now, if we just write it like that, that is fine. Now we're going to go back the other way and say, what do you think will be the two most common mistakes that students will make? Okay? But now, let's hold that thought. Okay, so there's our formula again. Okay, if we were looking for the energy, what do we have to do to the velocity? We need to square it. But if this is just the opposite, where we have this is a constant, we have this, and we're solving for our velocity, once we've isolated that variable, what is the last step you need to do? Just because you found the velocity, that doesn't mean you're done. We don't square it. We will. That could be a common mistake. We'll forget to divide by 2. But if we multiply two numbers together to undo that, we divide. But how do we undo a square? In other words, we need to find the root of it. In other words, we know that, for instance, 25, we know is 5 times 5. If we square 5, we get 25. But how do we know that that is 5? In other words, if we take the square root of 25, it just gives us one of them. And do we know what the square root symbol looks like, correct, on your calculator? Of course, it's this. It should be a common, no, it's not a common function on here. So above your 7, up 1, and to the left, if you have a TI-30X, okay? If you have a calculator like this, doesn't matter the color. But if you have a graphing calculator, it might be a little more complex than that, okay? But we can't, like for instance, this 25 we were talking about. We can't just take 25, hit this key here, and then hit equals. It's going to come up as syntax error because you didn't tell it the appropriate function to do. Okay? But if we do this, if we hit the second key, then above the 7 and to the left 1. You hit that because now we're changing the function of that, and then this symbol shows up. And it's waiting for you to type in whatever number it is that you want to take the square root. So then you hit 25, and lo and behold, you would come up with 5. Something's not right here. I'm not hitting the... Oh, I'm doing a cubed root. No wonder. So it's right next to the 7 key.
Yep.
Okay. Right idea, but wrong spot. So my mistake, your fault. Okay. I don't know. See how we pass that blame along? And we can blame it on other people and they don't even realize it. That's just really being good. Okay. So now, let's do what this formula tells you to do. We heard something about multiply by 2. You can do that, or you can multiply by 1/2. It's whatever one you choose to do. We put these variables in where the formula tells you. 3, 1, 2, 1.20 equals our mass, which we have 1.35 v squared all over 2. So how do we get rid of this fraction? You can, and that's fine. We put this over 1. What is 1 times 1.35? What is 1 times 1.35 v squared? Okay? So whatever this is multiplied by each other is going to equal whatever that is going to equal times each other. So we've got 1.2 times 2 gives you 6,442. No, 6,242.40. How do we get v squared by itself now? We want to divide each side by 1.35. Okay, so now we're going to divide that by 1.35. Then we get 4624. Now, v squared equals 4624. Okay, and this is what we were talking about. This is a mistake that students may make. We want the square root of that number. That's how we undo the square. If we square root this side, we have to square root that side. So what you can do is you can hit second next to the 7 key, the square root, and second and answer, and you should get 68. That was by design. I didn't want that to be one less. Okay? Darn it, I know. So we take the square root. Velocity equals 68 meters per second.
Then you minus 1.
Only in your world you would minus 1. All right, so that's all I have. We'll catch up to you next time.